All right. So I want to continue talking about how to go from modular forms to Galois representations. So remember, this is kind of one direction. When you think about modularity, it's like you want to kind of connect elliptic curves and modular forms. And one preliminary direction that you have to have is to go from a modular form to a Galois representation. And I want to just recall the theorem that we ended with on Tuesday. So we start out with S, a modular form of weight 2, and this level K naught n, and with complex coefficients. And K naught n is, you're thinking about matrices that are upper triangular modulo n. So it's this kind of congruent subgroup. So we take something here, and we assume that it's a normalized eigenvalue. And so that's something that we talked about last time. That's really important is we don't want to just take any modular form, but what we really want to do is think about the action of Hecke operators at primes that don't divide n, and think about simultaneous eigenvectors for those systems, for those Hecke operators. So I put here TP and SP, where P doesn't divide n, runs over those primes. You have an action of the Hecke algebra, and you can extract like you can diagonalize all the Hecke operators simultaneously, and then you think about eigenvectors. That's what these eigenforms are. And normalized just means that we're assuming that the first Fourier coefficient is 1. And then so you can maybe write f of z as sum from 1 to infinity of an q to the n. And the first thing that we talked about was that if you look at q and you adjoin all these Fourier coefficients, and I said that the Fourier coefficients are also happen to be Hecke eigenvalues, then what you get is a number field. So then this is a number field, so a finite extension of the rational numbers. That's the first claim. And then the second claim is that whenever you take a prime in this number field, so this is going to divide some rational prime L. In here, there exists a unique two-dimensional, irreducible, continuous representation that depends on the modular form F and on the prime lambda, and it's a representation of this absolute Galois group 2, and it's valued in this kf lambda, which is kind of, it's an L-adic field. So it could be QL, or it could be some finite extension of QL. Okay, and this is a global Galois representation going from F to KF, going from F to this system of rho F lambdas is one of the directions in the global Langlands correspondence. Okay. Yeah.
Can you remind me how L is quantified?
How what, sorry?
L is quantified.
What do you mean? So L is a prime, and this should hold true for any prime. So any choice of rational prime. So in particular, you know, the P's that we look at here have to be prime to n. But the L you should allow the L to also divide n. We should have, a whole compatible system over every prime. And I guess, I mean, one way to think about it is, in the case where this modular form really matches with an elliptic curve, so when that happens, when KF is just Q, then when you have an elliptic curve, you can talk about its L-adic tape module for any prime L, right? You can look at L torsion points, L to the n torsion points for any prime L. And so that's why you should get one for each. And so such that for any P that doesn't divide N or L, this rho F lambda is unramified at P. So you restrict it to the decomposition group of this at P, so to the local Galois group of the p-adic field, then this is unramified. And that just means, well, it's determined by one matrix. It's just determined by what it is on the Frobenius at P. So this, and the characteristic polynomial of the matrix, rho F lambda prop P, is x squared minus APX and plus P. Right, so the point here is that we recover, as the trace of this matrix, we recover this AP, which is the P's Fourier coefficient, and it's also the eigenvalue of the Hecke operator TP. Right, this F is a simultaneous eigenvector, and the eigenvalue of TP on it is AP, and that somehow gets remembered on the Galois side. I want to mention that for simplicity, I'm sticking with 2 here. But in fact, this theorem is known for any modular form of weight at least 1. And I'm going to give you more details about how to construct this Galois representation. And I guess the very similar argument works for any k that is at least 2. And then in the special case where k is 1, there's a result of Deligne and Serre, and the construction is different. The construction uses congruences to higher weight. So the remark, right? So this is a theorem, and I'll put due to Eichler, Shimura, and Deligne. And I'll put as a remark that the theorem holds actually holds for any weight. K at least 1, except you have to modify the characteristic polynomial. You have to incorporate, so with minor modifications. You have to incorporate the weight into kind of the determinant of this matrix. But in the case where k is equal to 1, the result is due to the Deligne-Serre, and this really uses congruences. So you first have to prove it in weight at least 2, and then you have to construct, so uses congruences to forms of higher weight. And so this is the kind of where we were last time. Are there any questions about the statement of the theorem? Yeah.
Could you just remind me what it means for the representation on GQP to be unramified?
Yeah, so basically, QP is this local field, and it has a ring of integers ZP and residue field FP. And there is a short exact sequence. So GQP, so if you act by an element of the absolute Galois group of QP, that induces, so on QP bar, that also induces an action on FP bar, and an algebraic closure of the residue field. So there is a map, which is actually a surjection from the absolute Galois group of QP to the absolute Galois group of FP. And the kernel of this map is called the inertial subgroup at P. And Unramified means that the representation is trivial on inertia, so it factors through the Galois group of the residue field. So unramified is factors through GFP, the absolute Galois group of FP, and this itself is just isomorphic to the profinite completion of C, and is topologically generated by one element, which is this Frobenius. And maybe one more thing for people who didn't encounter this concept before, if you're in the case, for instance, where you have a curve, like an elliptic curve or a higher dimensional algebraic variety, if that has good reduction, if that is smooth when you think about it over the finite field, then typically say, if in the case of an elliptic curve, the L-adic Tate module of that elliptic curve is going to be unramified. So there's this very kind of number theoretic definition, trivial on inertia, but then there's also this other way of thinking about it, which is that it kind of sees the primes of good reduction. Unramified means you're looking at a prime of good reduction. Any other questions? Okay, so I want to kind of discuss some steps that go into the proof of the theorem so that you have a sense for, how we go from the modular form that lives on this Riemann surface. So remember, we had this, I think I called it xk naught, right? This was this double quotient where I would take h plus minus cross GL2 of the finite adels, quotient it out by the level, quotient it out by GL2Q. And really it's just a disjoint union of, say, H mod gamma, where you run over some finitely many arithmetic subgroups like this. So that's what this looks like. This is some Riemann surface. And F in S2, K naught N, C is really, can be reinterpreted as a holomorphic differential on this space. So the space is a Riemann surface. It makes sense to talk about holomorphic differentials. And the kind of the symmetries that the function satisfies are cooked up in the precise way so that that's what it gives you. Okay, but so this is kind of where we start. And then we want to go to this Galois side. We want to kind of get to arithmetic geometry, to number theory. And so the first thing that I'm going to do is going to be just a technical thing that you can mostly ignore, which is that sometimes at this level, things can be a bit stacky, or like, if you construct, for instance, the fundamental domain, you might have some points where you have some sharp corners. And so just for technical reasons, I'm going to assume that n is at least 3, and I'm going to go to some slightly deeper level. I'm going to define the level K1 of n to be given by matrices in K naught n, but where I'm really requiring this gamma to be a bit more than just upper triangular. I want it to be congruent to 1 in this corner, modulo n. And so when I do this, I just want to kind of, go to a space that's a bit higher and kind of rigidify things a little bit more. And that will be more useful when we start talking about kind of algebraic geometry and moduli problems. It'll have a nicer structure. But it's just a technical step that doesn't matter very much. And we're going to view F as a form on this level K1n, still with complex coefficients, but I'm going to put here character. So basically, you have xk1n is a covering. When you make the level smaller, you go to a covering space. So you impose a congruence condition, you make the level, well, in some sense bigger, but in some sense, so you go to this covering space, and what you see here is a Z mod n Z cross. So if I want to think about some differential here, I could pull it back and think about a differential here, and I just want to remember that it was coming from here. So the way that you would do that is kind of remember a way of descending it. For that, you just kind of have to put a character of Z mod n Z cross. The character that I'm going to put is the trivial. Well, that's what I need in order for it to descend. In general, I might, if it doesn't descend, I might put a non-trivial character. But so it's just a bit of a technical thing that I need in order to rigidify the situation. Okay, and so we're going to think about it really as a holomorphic differential now on xk1.
Anna, can I ask why is it like star on like the top row? Isn't it like 1, 0, 1?
1 star 0, 1?
No, 1, 0, 1, like the star is only on the top right hand.
Sorry, I don't see where.
No, I think she's expecting 1 star 0, 1.
You're expecting 1 star 0, 1. Is that right?
Yes.
I think that this is enough to get a moduli problem that's representable. So I could go to 1 star 0, 1. I can always go higher, right? But I think this is good enough. I just want to have like a moduli problem that I know is representable.
I see, but I guess the normal like gamma 1 n is defined, I think the definition is 1 star 0, 1.
But on SL2.
On SL2.
Okay, maybe a big SL2 fixes the.
Yes, yes, right. If it's SL2, then it's forced, if I have a 1 here, it's forced to be a 1 there. But,
okay.
But I want to do GL2 because I want to talk about, well, these Heck operators that are P001, which are not in SL2. Okay, so this is kind of step 0, just a small technical thing. Step 1 is more interesting, which is that, so I kind of have alluded to this maybe a bit in the first 2 lectures, which is that something really special happens when your locally symmetric spaces have a complex structure. So in particular, for GL2 over Q, if you get Riemann surfaces, something special happens and you have a connection to number theory and arithmetic geometry. And for instance, for these Bianchi manifolds that were hyperbolic 3 manifolds, for those you don't have that. You don't have a complex structure and you don't have a further connection. And so the special thing is that they're not just complex manifolds. In fact, they're really defined over number fields. And the reason why this is because you have a moduli interpretation for these spaces. They represent a moduli problem, and this moduli problem makes sense over the rational numbers. So step 1 is to show that xk1n has a moduli interpretation. Namely, and from this, you'll get a structure, say, over the rational numbers rather than just over the complex numbers. In fact, to get even better, get a Z1 on n structure. So I'm just inverting these bad primes that are dividing the level. And other than that, I get even an integral structure. And the idea is as follows, that there exists a smooth affine curve that I'm going to call SK1n. The reason I want to call it S is S for Shimura of right. So this phenomenon generalizes that your locally symmetric spaces that have this complex structure, in fact, come from number fields. This generalizes to higher dimensional varieties that are called Shimura varieties. So there exists a curve like this over spec Z1 on n. So with coefficients in Z1 on n, you can think about the, kind of equations that would cut it down. And which represents the moduli problem So the following moduli problem. So for any scheme T, again, over spec Z1 on N, I'm interested in sending this to the set of pairs EQ, where E over T is an elliptic curve, and Q is just this sort of extra structure that I'm adding to rigidify the problem. It ends up being a point on the elliptic curve that's killed by N. So an N torsion point on the elliptic curve, a point of exact order N. Okay. And all of this up to some equivalence, up to pairs that are isomorphic. Okay, so what does this mean? Well, you can think about it roughly as saying that there is a curve with coefficients in Z1 on N, and which is basically a universal family of elliptic curves equipped with a universal point of exact order N. Or it means that, I guess, whenever you sort of probe your curve with some kind of test object T, what you get out is this set. So an elliptic curve, you have to think about over this scheme T, you have to think every fiber is an elliptic curve. So there's kind of a universal family. Whenever you probe it with some other scheme, you pull back this universal family, and sort of any family of elliptic curves over T corresponds to something that comes from the universal one. And with the property that SK1N, so this is defined over Z1 on N, I can think about it over the complex numbers. I can look at the associated Riemann surface, and this matches with the one that we started with. So what this is saying is we have this Riemann surface that we want to understand, and there's an integral structure on it. And this integral structure is in fact more powerful because it even kind of, it's a modular of elliptic curves with extra structures. It comes with a family of elliptic curves with a universal extra structure. And this is going to allow us to talk about these modular forms instead of just holomorphic differentials on the Riemann surface. It's going to allow us to think of them as sections of line bundles on this algebraic curve. And that is already a much more algebraic geometric object. And in fact, really, you have this kind of integral structure on it as well. Okay, so the fact that we have a family, as I said, means there is a universal object. So we have a universal elliptic curve, E, living over SK1N, and there's a universal identity section. So remember the elliptic curve that has this group structure, so it makes sense to talk about the identity. There's an identity section here that I'm going to call E. And then we can define the line bundle omega that you get by pulling back under this identity section the sheaf of relative differentials of this elliptic curve over SK1N. There's a notion, an algebraic notion of differentials that you can make work in families. And this is going to be a sheaf over here. Because an elliptic curve is smooth, that means this sheaf is actually very nice. It's locally free, and in fact, it's locally free of rank 1. So it's a line bundle. And then you end up pulling it back under this identity section. So this is a line bundle on SK1N. I should say this is like smooth, relative dimension 1. Okay. And it turns out that you can now think of all modular forms, including, so weight k at least 1, as sections of the kth power of this line bundle. And so now you get a much more algebraic geometric definition of the notion of a modular form. So let me just write down. A minor technical point is that you can actually compactify this even over Z1 on N. And the line bundle also extends to the compactification. So these structures extend to a compactification, so a projective curve. Right? You can think of, like, you have this affine curve, maybe like an affine line, and then you compactify it, you look at projective space. SK1N star, again defined over Z1 on N. And then you can identify the space of modular forms of weight 2 and level K1N with complex coefficients as global sections on this projective scheme, base change to the complex numbers with coefficients in the square of this line bundle omega. So it looks like I haven't done very much, right? Because we already had this space, and here I've base changed it to the complex numbers. But now the point is that there is a natural Z1 on N structure in here, which is just H0 of this without, right? So this is a Z1 on N structure. So by having this moduli, by having access to the moduli problem that's defined over Z1 on N, you also get the C1 on N structure on the space of modular forms. And now the same thing also happens with the space of cusp forms. So S2, it's the same thing, it's just S2 instead of N2. And then I have to impose zeros at cusps. So H0 on this compactification, tensor of omega, and with zeros at the cusps. The cusps are just points. So if you remember the picture we drew in the beginning, right, we were just missing these points at infinity. Kind of the same thing happens when you compactify it over Z1 on N. You just add some points, and you have this structure in here. And this is also very useful for, it gives you a good way to talk about congruences between modular forms, because it gives you a good way then to, well, think what would be a mod P modular form. It would be something like this, where I reduce mod P. Okay. So this is step 1, getting close to an integral structure. Are there questions about what's happened here? Yes.
Just a very random question. You mentioned we can think of the mod P modular forms by essentially taking the reduction mod P. So I'm wondering, is it possible to think, for example, about p-adic modular forms as some inverse limits in some way related to this?
Right, you can get to the point of talking about p-adic modular forms. But so when you want to do p-adic modular forms, part of what you want to do is you want to allow your weight to vary p-adically as well, right? So, and what I've done here, my weight is kind of fixed. It's an integer. and I want to allow a p-adic weight. If I want to allow a p-adic weight, I would have to find some way of trivializing the line bundle omega. Just like, if you do completed cohomology, and you have to trivialize the local system in order to vary the various weights. And you cannot do the omega, you cannot do this over the whole integral model, but you can do it over part of it. And so this is why you see the ordinary locus and the Igusa tower. Sure. Maybe I want to, while people think if they have other questions, I want to mention that this kind of, so I'm not going to prove that this xk1n, is recovered by having this moduli problem and then looking at the moduli, what it gives you over the complex numbers. But at least at the level of points, there's an exercise in the sheet of problems that Alice has come up with that allows you to see about what different moduli problems, what structures different moduli problems correspond to. And you can write down some things like this over the complex numbers and at least check that, the points here, so the elliptic curves over C here, with a point of exact order n, really match up with the right quotient of the upper half plane. So that's something that can be done by hand. You need a bit extra to say that things vary nicely in families. But yeah, so this is something that you can do concretely. And ultimately what it amounts to is really thinking about what is the upper half plane a moduli of? Like, you need a moduli interpretation for the upper half plane itself. And so there's something in Alice's problem session about this that gets you started. The way that I like to think about it is I like to think that the upper and lower half planes are moduli of Hodge structures of elliptic curves. So it doesn't fully remember the elliptic curve, but it remembers the Hodge decomposition on H1 of the elliptic curve. So if you saw Mingjia's colloquium talk yesterday, she talked about Hodge theory and what the Hodge decomposition is. And that amounts to, so having a Hodge decomposition on this complex vector space, it's not that far from just having a different complex structure. And that's what the union of the upper and lower half planes do, is they give you different complex structures, right? The natural one is to choose I as your complex, as giving your complex structure, but anything that's not on the real axis will define a different complex structure. So that's the interpretation that I like the most. That kind of gives you a conceptual connection between kind of the space we're looking at, the union of the upper and lower half planes, and some moduli problem of elliptic curves. Okay, any other questions about this step? Yeah.
Could you explain what a universal elliptic curve is?
So what it means is that if I want to probe this space with my T, then I can pull this back and I get a family ET over here. That's something I can always do. I can form the pullback. And the fact that it's universal tells you that whenever I have some other T primed and a family of elliptic curves over it, with T primed mapping in here, then there's a unique way to complete this to a Cartesian diagram. And so it has this very strong property that it sees all families of elliptic curves that you could imagine. Yeah.
Right behind you, when you talk about the Z1 over N structure,
yeah.
Can I just, so I can keep track, it's like a complex vector space and inside of it, there's some sort of Z1 over N. So
right. There's something defined over Z1 on N, such that if I tensor over Z1 on N with C, yeah, I get the complex vector space. Right. Okay. So this was step one, and we're actually making progress. We're almost at the point of seeing that KF is a number field. That's going to be step two. So in order to do that, oh, and maybe I shouldn't have erased this. It's okay. Yeah, oh well. So let me use this. my F is an element in here, right? And I have this heck action over here, or over here, and F is an eigenvector, a simultaneous eigenvector. And I want to know that the eigenvalues are algebraic numbers. This is some finite dimensional vector space over the complex numbers. If I can get my heck operators to act on this Z1 on n structure, then I will know that the eigenvalues have to be algebraic numbers. Something, maybe you can think about it a little bit, but let's say you have an operator on a finite dimensional Q vector space, right? Then that matrix satisfies a certain characteristic polynomial, and the eigenvalues are roots of the characteristic polynomial. If the matrix is defined with Q coefficients, then the characteristic polynomial has Q coefficients, and that means the eigenvalues have to be algebraic numbers. So that's the kind of phenomenon that we want. And so the only thing that we need now, the only thing that's left is show that the Hecke operators also act integrally on this Z1 on n structure. So step 2. Construct. So let's say let P be prime. Construct TP and SP on S2 K1 on N. On the integral. So with zeros at the cusps or without. I have an integral understanding of what the Hecke operators are. And for this, you just need an integral correspondence. Right, if you remember, we had xk1 n, and if I want to talk about TP, I would intersect this with k naught p, and then there was a map P1 that was the natural projection, and then there was another map that kind of involved the action of P001 followed by the natural projection. Right, so this is over C. And you want a version of this diagram over Z1 on N. And if you have that, then you get your Hecke operator TP. And similarly with SP. The SP is always a little bit simpler than the TP. Okay, and so we want possibly with the cusps as well. That's slightly less important. This is now over C1. And as it turns out, again, there's a moduli problem of elliptic curves with extra structures that is representable, and such that the representing object fits into such a diagram. And you can write down these maps moduli theoretically. There exists right. So what? So there exists an affine curve, no longer smooth, as K1n intersect K naught P over Z1 on N, which represents the moduli problem. And the thing is that by doing the exercise over the complex numbers, the one in Alice's problem sheet, you can figure out what it should be. So T goes to, you just have to add some extra structure that encodes what this K naught P is. So some covering, you rigidify the problem even further, E and Q and C, where, so E and Q are as before. So they're in SK1 on N, T, so as before. And now C is, basically, if we were doing this over the complex numbers or even over the rational numbers, or even over spec V1 on N with P inverted, all we'd have to say is a subgroup of order P inside the P torsion. That's what it matches with. Because we want to do this even when we allow P, so we want to allow even to send P to 0, so we want to kind of not remove this point. We want to kind of think about the reduction mod P as well of this moduli problem. We're going to have to say that this is a subgroup scheme, a finite flat subgroup scheme of order P inside. So you look at the P torsion of the elliptic curve, that itself is a finite flat group scheme over RT. And inside there, you want something of order P. So this would be like order P squared, and you want to kind of choose that structure in a family. Okay, and then it turns out that you have a description for what P1 does and what P2 does. So over here, I have E, Q, and C, and this is the forgetful map. So I just forget the extra structure that I've added at this level K naught P. So I forget the C. This just gets sent to EQ. That's P1. And over here, I have to do something more interesting. And the interesting thing that you get to do is you get to divide by C. So you go kind of from one elliptic curve to an isogenous one that you obtain by dividing by this subgroup. So this is E primed, Q primed, where E primed is E mod C, and Q primed is Q mod C. So Q is a point of exact order N is prime to P. So if I look at it modulo this, I look at its image in E prime, right? So you think about it as sort of the image E to E prime is an isogony. And I've had my point here, I map it to Q prime, and here, this is still a point of exact order N because the kernel of this isogeny has order prime term. Okay, and so, yeah, it's really nice. You get basically this moduli theoretic description for these Hecke correspondences. And so at this point, yeah, we're basically done with understanding why KF is a number field. Because, for instance, you can look at it over Q. You have a finite dimensional Q vector space with a bunch of commuting operators that can all be simultaneously diagonalized. And then it's just the statement that the eigenvalues are algebraic numbers. And in fact, they all can be diagonalized over some specific finite extension of the rationals. Okay, so this was step 2. Any questions about this? Yeah.
Is it some linear algebra thing that they can all be diagonalized by the same matrix, or is it some deep number theory? They can all be.
It's okay. I will say it's not quite only linear algebra, but maybe linear algebra was a bit of commutative algebra, maybe. Because the point is that you should see, like, a priori, this is some abstract Hecke algebra, but you should look at it inside the endomorphisms of this vector space, and then it becomes something that's, you know, like finite over Q. And once you know that, then you're good. So a little bit of commutative algebra, maybe. Linear algebra and commutative algebra. Okay, so yeah. So we already deduced that KF is a number field. And if you haven't thought this through before, it is good to convince yourself that this does work. Okay, and we have time maybe for one more step. And well, actually, maybe we have time for me to draw. I have a very pretty picture that I want to draw. I hope to be able to end with a very pretty picture. And then we can discuss what it is during the last lecture. So step 3 is gonna be the step where we actually construct the Galois representation. So far, we've taken our modular form and we've passed it through these various cohomology theories and kind of gone from analysis to really arithmetic geometry and getting it kind of showing that the coefficients are algebraic. But the thing that we're going to do now is actually construct a Galois representation. Maybe I do want to mention that even in this case, there are some highly symmetric functions that are similar to modular forms, but that aren't modular forms, that are called mass forms, where even this step is a complete mystery. So for GL2 over Q, there are some kind of, I don't know, evil twins. I don't know what the right way to say it is, but there's something else that's like modular forms, but that cannot really be viewed in cohomology. And for that reason, we don't know this kind of result for them. So that's a really big open problem in the field. Okay, so step 3, this is called the Eigler-Shimura isomorphism. And this is what's going to allow us to construct our Galois representation. And first, you just have a statement over the complex numbers, and it just comes from the Hodge decomposition. So if you've seen the Hodge decomposition even just yesterday, it's just an instance of that up to a minor technical detail. So there is a T equivariant isomorphism. So we have our, maybe I'll start on the side of singular cohomology. So we have our space, and I can write it as the Riemann surface. I mean, I could put here S of C, but it's just the Riemann surface, the quotient of the upper half plane or union of several kind of quotients like this. And I can look at its singular cohomology. So you can think of it, okay, it's a Riemann surface, so it's like some kind of space that you get with a bunch of handles. And the singular cohomology remembers how many handles you have, right? Remembers how many holes there are. So this is a vector space over the rational numbers. And you can extend scalars to the complex numbers so that you get a complex vector space. Right, so this is the kind of thing that shows up when you think about the Hodge decomposition. You might start out with a singular cohomology of a variety, but viewed as a complex manifold, and then you extend scalars, and then you can connect it to pieces that come from de Rham cohomology, from differentials. And so that's what's happening here. This ends up being a sum of M2, so modular forms that aren't required to vanish at the cusps, of weight 2 and with coefficients in the complex numbers, and plus S2 K1N C, and this is the complex conjugate of it. So that's a theorem due to Eigler and Shimura. So think about, as a kind of think about the Hodge decomposition. Which is if X over Q is a smooth projective variety, then H1, the singular cohomology of the complex manifold, if I tensor to this, breaks up as H0 of X, say over C, omega 1 XC plus H1, if you haven't seen this before. But somehow it's really kind of about comparing things that look like pieces of de Rham cohomology with singular cohomology. And this idea that, you know, if you have a space that can be viewed as a kind of from an algebraic point of view, or it can be viewed as a manifold, somehow you should be able to compare the different cohomology theories. So I said, think about this. I didn't say this is the proof. Does anyone sort of notice what's missing? So that, why can't I just apply this? And this itself, this is the complex conjugate of H0. And so I could write it like that. So what's missing? Why can't I just prove it like this?
How are you going from weight 1 to weight 2?
Well, that in itself is not such a big problem. So these are the big differentials on X. So this is secretly weight 2 forms. Weight 2 forms are holomorphic differentials on X, even though they're sections of this little omega squared. So there's, in fact, omega squared matches up with big omega. Little omega squared matches up with big omega. So that in itself is not such a big problem. But one thing is that this space is not compact. So SK1N is not, but, right, subtlety, because SK1N is not projective. So it's smooth, but it's not projective. And for that reason, when you write out the decomposition, you don't actually get symmetric pieces. You get a bigger piece plus a smaller conjugate of a smaller piece. And there's also a version for cohomology with compact support that looks different. And you have to kind of look at the image of cohomology with compact support and usual cohomology to get something symmetric. So just the fact that this is not projective is what makes it more subtle to see what's going on in this case. But if you had something that was projective, then such a result would amount to Hodge theory, to the Hodge decomposition. Okay, so what you can do now is you can try to track down F. Instead of looking at F in here or in here, you can look at it in singular cohomology. And so how do you do that? Because F is, you know, it's a holomorphic function. How do you view it in singular cohomology? This is the point where we again really need to use the fact that we're working with an eigenform. We don't remember F itself, but what we remember is the system of Hecke eigenvalues. So F if F in here is an eigenform, then it determines a system of Hecke eigenvalues. And then that means it determines, so it's slightly just a conceptual step, but not too bad to think of it as a maximal ideal inside the Hecke algebra, say tensored over C with C1 on it. So if TP goes to AP, which is some complex number, then I can take this Hecke algebra, which is Z adjoined TP, and I can just send it to C by sending TP to that complex number. And the kernel of that morphism is going to be a maximal ideal in here. Okay, and so what we're going to keep track of is we're going to keep track of this maximal ideal. And the way that we want to do it, so that's one thing. So instead of working with F, we're going to work with the system of Hecke eigenvalues from this more commutative algebra perspective. We're keeping track of the maximal ideal. But so we want to look at kind of the space cut out by MF So over here, I have a Hecke action too. And this isomorphism is Hecke equivariant. So I can look at kind of the eigenspace for MF in here, instead of looking at it in here. What's the dimension of that eigenspace going to be if I start out with a cusp form? It's going to be 2, because there's this multiplicity 1 result that says once you know the system of Hecke eigenvalues, you've determined your modular form. So it shows up once here, but because a cusp form is in particular a modular form, it'll also show up once here. So the eigenspace, if I cut out the eigenspace for this particular system of Hecke eigenvalues, I get something 2-dimensional. So that's already promising. It starts to look like the Galois representation that we're looking for. Except there's a big problem that, well, where does the Galois action come from? And then you have a third cohomology theory that you need to use, as it turns out. And the cohomology theory that will give you a Galois action, this is something that came up in the first lecture. There's this like amazing machinery developed by Grothendieck and his collaborators that will give you Galois representations if you start with algebraic varieties defined over number fields. And so if we have our SK1n, to get a Galois representation, we have to work with the étale cohomology. Okay, so now we have to put it together a little bit. The way that we're going to do this is we're going to choose an abstract isomorphism between C and QL bar, inducing sort of prime. So our KF, we view it naturally in here. And when you view KF via this abstract isomorphism, when you map it in here, it's gonna induce a prime of KF dividing L and inducing the prime lambda of lambda dividing L of KF. So it just means that you have to be a bit careful when you take your number field about how you would embed it into a big elliptic field. And you want to choose it so that it matches this thing that we've kind of chosen in the statement of our theorem. We have some lambda, and we want to come back to that lambda, and we want to be careful with the embedding so that it really gives the lambda. Okay, so we choose an abstract isomorphism like that, inducing this prime, and now we look at the étale cohomology. And in fact, we define rho f lambda to be, so you look at H1 étale of SK1n over Q bar, so over an algebraic closure of Q, with coefficients in QL bar, and then you take the MF eigenspace. And so this is what our rho f lambda is, because this étale cohomology comes with an action of GQ, and so we get rho f lambda from GQ into GL2 QL bar a priori. And then you have to kind of show that it factors through GL2 KF lambda. You have to show that it's unramified at P if P is a prime that doesn't divide N or L. And you have to show that the determinant of X minus rho f lambda from B is X squared minus AP X plus P. So you want to show that the TP eigenvalue shows up on the Galois side. That's what's left. Okay, so I'm not going to have time to draw my picture, but tomorrow we're going to start with what I think is well, one of the prettiest pictures that I get to think about. And that's gonna, well, we're gonna figure out how to do these last three remaining things. And then we're gonna talk a bit more about what there is out there in this world of modularity and the Langlands correspondence. All right, are there questions? Yeah.
Let's just double confirm for the L here, is there any restrictions on the L's we can choose or not?
No, there is no restriction on the L you can choose. Yeah, you should be able to choose every L. And every lambda above it. Yeah.
Despite this construction, it's not so clear that this representation would match up from the Tate module, right? Coming from the elliptic curve, just by seeing this.
You're absolutely right that this is in no way clear. Yes. One thing is that sometimes this space already will be an elliptic curve. So in certain cases, it so happens that your modular curve has genus 1 and it's an elliptic curve itself. And then it's a little bit simpler. Then this relationship does tell you that it matches up with the Tate module because the H1 et al is just up to taking dual, it's the same as the Tate module. So in that case, it's, but if you just have a random elliptic curve that you want to show is modular, yeah, it's not at all clear. That's right. All right, so yeah, we'll start with a pretty picture tomorrow.